Hello and welcome to Gaffy's Grinds. You're very welcome back if you're rejoining us. And if this is your first time watching the video, you're very welcome. But I suggest that you do not start with this video. Go back and watch this sequence in order. So on heats of reaction, there is a full playlist and you should watch them in order. The usual reminders to stick your phone on silent or better still, turn it off or put it in another room where it can't distract you. And the usual reminders, make sure you do the tasks that I ask you to do in the video. Today's video is on Hess's Law. Before I tell you what Hess's Law is, we're going to just build up to it a little bit. So, quick reminder of some of the things we're talking about. We are speaking always about chemical reactions. And say we have a chemical reaction where we've got A plus B producing C. So A plus B producing C. So first of all, I would like you to speak your answer to the screen. When I ask the question, that's how I would like you to answer. I would like you to tell me, what are the reactants in this reaction? Okay, I'm hoping that you said the reactants in the reaction are A and B. So whatever's on the left are reactants and whatever's on the right of the arrow are the products. Now, we talked already about considering energy changes in a chemical reaction, and we can kind of consider the energy of the reactants and products to be kind of like a battery. Now, why am I comparing them to a battery? Well, a battery stores energy. It's got energy in what we call a chemical energy store. So a battery stores energy. And we know that some reactions start with the reactants having a certain amount of energy stored. So A and B have a certain amount of energy stored between them. So this is what we call an energy store. So this is chemical energy or energy in the chemical store. So imagine a scenario where we've got A and B and they're storing this amount of energy. Now this here is a pretty small amount of energy. It's a pretty small amount. And say then we consider that we end up with a situation where we've got C, which obviously is also storing energy because it's a chemical. It's got energy in its chemical energy store. But all of a sudden we now have a lot more energy being stored in the bonds of this particular chemical. So A plus B gives us C. Now, the question is, where did this energy come from? Was it created? There's extra energy there. So it's a fair question to ask, was it created? And we have already learned that no, it was not created. What happens is that energy, during the chemical reaction, energy is taken in or is transferred in to the system. And where does that energy come from, or where is it transferred from? So on 3, speak your answer to the screen. What does the red arrow show? Energy moving from where? Where is it coming from? Okay, so on 3, 1, 2, 3. Okay, so I'm hoping that you said energy comes from something called the surroundings. And the surroundings is just everything except the reacting chemicals. So if it's not the reacting chemicals, it's the surroundings. It could be the room, it could be a container, it could be a liquid that surrounds it. It could be anything. It could be a thermometer, it could be a glass container, but it's definitely everything that's not the chemicals that are reacting. So energy is taken in from the surroundings. So it's not created, it's just transferred. It's already there in the surroundings. It just leaves the surroundings and enters the reacting chemicals. Similarly, if we take our reaction, and this time we consider a reaction where the reactants are storing a lot of energy. So this time, I'm just going to change the color here. I'm going to choose orange. This time, A and B store a lot of energy. Like this. And C stores a lot less energy. Now, again, this shouldn't be a really new idea to us. We've already looked at these types of reactions. But the question is, well, where has the energy gone? Has it been destroyed? And again, it's a fair question to ask. There is less energy there now. So did it just get destroyed? But of course, we know, no, it did not get destroyed. It is transferred out of the system to, where is it going to again? It's going to the surroundings. So I suppose the big idea here is that, well, energy is never getting created or destroyed. So energy cannot be created or destroyed. All that really happens is that it moves from one, or changes from one form to another. When it's been stored by the chemicals, it is what we call in the chemical energy store, or it's in the chemical energy form. When it's transferred then out to the surroundings, it's transferred to the thermal energy store of the surroundings, or it's transferred to thermal or heat energy. Okay, so there's a couple of ways we can look at energy, but it's all got to do with it either changing form or moving from one place to another. It's never getting created. That's the key thing. So energy is never created or destroyed. It cannot be created or destroyed. It only gets changed, only changes, or only changed from one form to another. So it's either stored inside the chemicals, or then it gets transferred as heat to the surroundings. That is change in form. It is not getting destroyed. This is what's known as the law of conservation of energy. And it's a law because it's always true. There's nowhere in the world where this has proved to be incorrect. And it has been tested over and over and over again. And it becomes known as a law. So a law is something which is tested over and over and over again, and it's not proven to be incorrect. So this is the law of conservation of energy. What I'm going to get you to do is I'm going to get you to pause the video and just take down the definition. Okay, so you should only be watching the video if you've paused and taken down the definition. And I would like you to cover over that now while you do these practice questions. So you've got questions 1 to 4. There is some recap revision in here. Okay, question 1 and 2 are definitely recap questions. Sorry, I'll just change the number of this. There should be 1 and 2. Okay, and what I want you to do is I want you to pause the video and do them questions now, please. Okay, so let's go through them really quickly. Okay, so you should only be listening to my voice if you have done the questions, and we are about to correct them. So you need your correcting pen, different color, and you have to write an equation to show the formation of MgCl2. So we practice writing equations for the formation of a compound before, and you're forming a compound from its elements. Now you're forming it, so it's a product and it's on the right. So MgCl2, I'm writing it as a product. I'm also making sure there is only 1 mole of it, because the heat or the formation, when we're writing the heat of formation equation, we're always writing it for the formation of 1 mole of the product. So I make sure it's a 1 in front of MgCl2. Everything else balances to fit that. Well, the elements that it's made of is just Mg plus Cl2. And luckily for us, that's already balanced. So magnesium plus chlorine join together to make magnesium chloride. What about an equation to show the combustion of this substance? So C3H6, this substance would be ethene. Oh, sorry, not propene. So you've got C3H6, and it's a combustion. So we want to burn 1 mole of it. Always making sure we're burning 1 mole. So this is going to be a 1 in front of this. And for combustion, we're always adding oxygen, and we're always producing CO2. Sorry, damn autocorrect. It's good when you're using it, but when you don't want it, it's a pain. So CO2 plus H2O. And again, I just need you guys to learn that now, that when you're doing a combustion, you're always burning with oxygen and producing CO2 plus H2O. You have to know that, otherwise you're not going to be able to get those correct. But I'm hoping that you practice enough of them the last time that you can get them. All right, so let's balance. Carbons. On the right here, we've got 3 carbons. On the left, we've only got 1. So I'm going to put a 3 here. That's carbons balanced. Let's check the hydrogens next. The reason why I'm checking the hydrogens next is I'm going to leave the oxygen for last, because it's by itself and it's easy to fix when it's by itself. So let's do the hydrogens next. I've got 6 hydrogens on the left, 6 here, and I've only got 2 on the right. So if I put a 3 here, that'll be 3 times 2, 6 hydrogens. Let's count the oxygens now. I've got 3 times 2 oxygens here, which is 6, and I've got 3 times 1 oxygen here, which is another 3. That's 9 altogether. I've got 2 here, so to turn this into a 9, I'll multiply it by 4.5 or 4.5. So that is a balanced equation there. Okay, now you might be tempted to multiply everything by 2 to get rid of this half. And normally that would be fine, but I can't do that here. And the reason for that is this is show the combustion of this substance. So the combustion of this substance, this has to be for 1 mole of this substance. So I'm not going to adjust this to get rid of that 4.5. I'm going to make sure that just stays here as a 1. So I'm not going to multiply everything by 2 to get rid of the half. Next one, a reaction produces a product with less energy than was contained in the 2 reactants. John says that energy has been destroyed in the process. Explain why this is incorrect. Right, so I'm going to type an answer in here. Explain why this is incorrect. Okay, so this is incorrect. And why is it incorrect? Well, we've broken something because the energy did not get created or destroyed, did it? So because the law of conservation of energy states that energy cannot be created or destroyed. So it has to be wrong. Now let's explain what happened instead. Well, the reaction produces a product with less energy than was contained in the 2 reactants. So energy didn't get destroyed, but there's less energy in the product. So where is the energy gone? The energy has been transferred. Where's it going? To the surroundings. So it doesn't get destroyed, it just gets transferred to the surroundings. Now, how would you know that that was happening? Well, if you were to feel that reaction, it would get warm. So you would hold it and you would feel that energy being transferred to the surroundings because your hands would be the surroundings. So it would feel warm to you, and it would also increase the temperature of a thermometer because the thermometer, if you put the thermometer in, the thermometer is the surroundings and the temperature would go up. What type of reaction do we call this? Speak your answer on 3 to the screen. 1, 2, 3. I'm hoping you said exothermic. So it should be, you should have said exothermic reaction. Right, complete the sentence. The law of conservation energy states that energy cannot be, right, so what is this going to be? This is going to be created or destroyed. So it cannot be created or destroyed. It can change from one form to another. So that's what you should have had. And again, don't forget to correct your work like this. So either tick it or fix it. So it's either right and it says exactly what it says there, or it says the exact same thing. Might have a word different here or there. And if not, then you need to fix it using your red pen. Okay. Now, okay. So again, we're just going to recap another idea, and that is, let's take, for example, we have our A plus B, and we're producing 2 products, C plus D. What substances are the products in this reaction, please? Speak your answer to the screen on 3. 1, 2, 3. You should have said that C and D are the products. So these are the products. And the reactants are on the left. We've got the reactants and the products. Now, we know that this reaction is going to have an energy change, or what we call a delta H, which means delta means change and H means heat. And heat is a type of energy, and this reaction is going to have a delta H. The question is, well, how much is delta H? Is it? What's the number? What's the value? And of course, it depends on what's going on in the reaction. So say, for example, A looks like this. It's got 1 green atom combined with 1 green circle atom combined with an orange triangular atom. So these represent different types of atoms. So the reactant A is made of a green circle and an orange triangle, chemically combined. Now, reactant B is made of an orange circle. So it's a different element again. I know it's orange, but it's circle this time, so it's different from the one in A. And its combined, or it's bonded to a blue triangle. Now, we know that during a chemical reaction, first of all, bonds get broken like this. So that bond and that bond have to get broken. Now, of course, that requires energy. So energy gets taken in from the surroundings to break the bonds. So we say that energy is coming in this step. So energy in. So if energy is going in, is this exothermic or endothermic process? Is bond breaking exothermic or endothermic? On 3, speak your answer now. 1, 2, 3. Okay, I'm hoping that you said it's endothermic because energy is taken in from the surroundings to break the bonds. And what that leaves us with is this. We've got now our 4 separate atoms, and they are separate. They are not joined together anymore. So we've got 4 different kinds of atoms. Actually, I'm going to say that that was a red circle. Okay, just so that it's clear the difference between them. We've got the red circle. So we've got the green circle, the orange triangle, the red circle, and we've also got the blue triangle. And they are separate. None of these are bonded together anymore. So we've got different types of atoms, and they're not chemically combined to each other. What do we have now? On 3, speak your answer. 1, 2, 3. Okay, I'm hoping that you've said we have elements. So we've taken our reactants, which were compounds, and we split them into their elements. And to do this, it took energy. What then happens is that the atoms recombine to form the products. So now we have our blue triangle, which is chemically bonded with our green circle. So blue triangle and green circle. And we now have an orange triangle like that. And it's chemically combined with a red circle like this. So we've got 2 different products now. Now, when these bonds are formed, energy is given out or is released. So bond forming, is this an endothermic process or an exothermic process? Speak your answer to the screen on 3. 1, 2, 3. I'm hoping that you guys said that this was exothermic because energy is given out. Now, if we take a look at a reaction that actually has some proper elements in it or has some proper chemicals in it. If we take, for example, SO3. Sorry, that's SO2. Sulfur dioxide. And this is a gas substance. And if we watch it, and it's going to react with 2 molecules of H2S2. No, H2S, and this is a gas, sorry. So we've got 2 gases reacting. So we've got SO2 and H2S. I'm just going to make that clear. I'm going to get rid of that and just rewrite it a bit clearer. That's a gas. And we're going to react it to give 3 atoms of sulfur, which is a solid, plus 2 molecules of H2O, which is a liquid. Now, we can consider this reaction here to have happened all in one step, like this route. We call this route 1, which is the direct step. Just SO2 plus 2H2S gives you 3S plus 2H2O. We can consider this as the reaction all happening in one go, similar to this arrow up here. We're not considering the step in between. And we know in reality what really happens is that bonds have to be broken to give you the elements, and then the elements rejoin to give you the products. But we don't always have to think of chemical reactions like that. We can just think of them as a one-step process. If we want to get a little bit more detailed about it, though, we can consider the more detailed, what we call route 2. And And when we consider the more detailed root 2, we have to figure out, well, what are the elements that are in here? What are the elements that are in the product, or the reactants here, sorry. Well, first of all, we've got sulfur. So remember, this SO2 is made of sulfur and oxygen. And if we look here, there's actually another sulfur over here. And in fact, there's two sulfurs over here, like that, because it's 2 times everything after it. So we've got, altogether, we've got 3 S's. We've got 3 S atoms. Plus, what other elements do we have here? We have oxygen, O2. Now, we've only got oxygen in the SO2. We don't have any in the H2S. So we just have O2. Plus, and what else do we have? We have hydrogen, and we have 2 H2s. So altogether, we have 2 H2s, like that. Now, why is this S? Why isn't this 2O like this, 2O? Well, oxygen is a diatom, which means elemental oxygen as an element, always exists as 2 atoms joined together. There's no such thing as oxygen atom, just one on its own. That's why this is O2, and hydrogen is the same. That's why every hydrogen has to be H2. So you've got H2 like this, and we've got 2 of them. So we've got 2 of these things. We don't have 4 separate H's like that, because hydrogen doesn't exist like that. Hydrogen exists as H2. It's a diatom. Okay, that's why those are O2 and H2. So we've got root 1 here, and we've got root 2. And the key thing here is it doesn't matter if you consider the reaction to happen all in one go, like root 1, or happen in 2 separate parts, like first breaking into the elements and then forming new compounds. That's root 2. It shows it more complicated. It really doesn't matter, because the delta H, the change in energy, will be the same. It will be the same whether it all happens in one step or it happens in 2 separate steps. Okay. Now, if we consider a second one, so I'm going to do a second one, and then I'm going to get you guys to have a go at a couple of them yourself. All right, let's take a look at this one. C6H12O6. Some of you guys might recognize that as glucose if you do biology. Now, glucose reacts with oxygen, O2, in the process of respiration. 6 CO2s plus 6 H2Os. And the delta H is equal to, well, we don't know what it equals to, but it doesn't matter. That's not what we're interested in right now. We know that this is what we call root 1. This is it. This is showing us the reactants and the products. But we know in reality, there is more going on behind the scenes. There is more steps to it than that. So root 2 is going to show us the steps more closely, root 2. So let's take a look at, see if we can write down what the elements will be. Okay, so first of all here, I've got carbon, and I've got 6 of them. Now carbon exists as a single atom element, so this is going to be 6 C's. That's easy. I've also got hydrogen, H2. So hydrogen is H2, and if hydrogen is H2, I've got 12 atoms of hydrogen altogether. So that's H12, 12 altogether. So that means I have to have 6 H2s. Plus, I've got oxygen, and oxygen is a diatom, so it's O2. And how many have I got altogether? I've got 6 there, and I've got 2 more there, so that's 8 altogether. So that would make this, I'm missing something here. This is actually 6 O2. I knew I was missing something, so I don't actually, that was going to be wrong. Yeah, this is O2, and I've got 6 here, and I've got 6 times 2, which is 12 here. I've got 18 oxygens in the reactants. That means I'm going to have 9 O2s in the reactants when it breaks up. Okay, so it really doesn't, like I said, it really doesn't matter whether I go in step one, in route one, which is just a single reactant turned into products, or if I consider it as a more detailed reaction where the reactants break down into their elements and then form new compounds. It really doesn't matter because the delta H is going to be the same either way. Now, again, we'll take a closer look at the reasons for that later on. Right, I've got one I want you to do now. Can you do this one for me? So C6H6 plus 3H2 to give C6H12. Right, what I want you to do, this should be a pretty easy one. What I want you to do now is I want you to write down the root 2 for me. So pause the video and see, can you write down the root 2? So where we form the elements first and then form the new compounds. All right, so pause the video and try to do that for me now, please. Okay, so you should only be watching the video if you have done root 2 for that particular reaction. Looks like this, root 2. So what elements do I have here? I have carbon, C6, and I have hydrogen. Those are my 2 elements. So I've got carbon and I've got 6 of them. So that's what you should have, 6C. Plus the other element here is hydrogen. Hydrogen exists when it's an element as H2. So altogether, I've got 6 carbons and I've got 3 times 2, which is 6 more. So I've got 12 hydrogens altogether, and that's 6 H2s. So that shows me the 2 elements that my reactants will break down into before they then form the products. Right, I've got another one for you to do now, one more. It's important that you practice enough of these before we move on. So try this for me. I've got 4 NH3s. This one's a little bit harder. Plus 7 O2s, producing 4 NO2 plus 6 H2O. Pause the video, try and do, I've done root 1. You try and do root 2 for me now, please. Okay, so root 2, this is what you should have done. We draw an arrow connecting root 1 and root 2. This is root 2 like this. And let's write down the elements that are in here. Well, first of all, we've got the element nitrogen. And nitrogen is a diatom, N2. Now you guys, I know the people in my class would know which elements are diatoms. The rest of you, if you haven't done this in chemistry before, I'll tell you them now, but you will come across them when you do bonding. We've got H2, hydrogen. We've got N2, nitrogen, O2, oxygen, F2, fluorine, Cl2, chlorine, and I2, iodine. Okay, so, and Br2, bromine. So actually, if you have a look on your periodic table, there's actually kind of a shape that it traces. First of all, we've got hydrogen out on its own. So very quickly, I don't really want to spend too much time on this, but we've got hydrogen out on its own as an element. And then we've got nitrogen, and nitrogen, oxygen, fluorine, kind of this shape on the table. Sorry. This shape on the table. We've got nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All those are diatoms, exist as 2 atom elements, or elements made up of 2 atoms always, never atoms on their own. This is because they're just too reactive. Once they're together, they will always bond with another one. They're just too reactive to exist on their own. Now, so that is nitrogen, so N2. We've then got, give me 1 second here, I'll have to loosen something that was important. Sorry, N2, and how many of them have we got? Well, we've got 4 nitrogens altogether. So we've got 4 times the nitrogen here, which is the same as 2 N2s. So 2 N2s plus I've got hydrogen. I've got 4 times 3 hydrogens, which is 12. So that will be 6 H2s. Well done if you got that right. And oxygen is already an element. So it is already done for you, plus 7 O2. So that's root 2, 2N2 plus 6 H2 plus 7 O2. Well done if you did that right. Excellent job. Now, I'm just going to make it a little bit more concrete now. And again, we're going to try and have a look at an actual chemical reaction to show you this. If we take the reaction where we've got, say, carbon plus oxygen, these are 2 elements reacting to form CO2, like this. Now, if we consider that this is root 1, it's just happening in one step. The carbon and the oxygen join together and they form CO2. Now, if we were to draw this, we would know the carbon is already a single atom, like that. And the oxygen is 2 separate atoms drawn like this. Or not 2 separate atoms, sorry, 2 atoms joined together like this. Well, what we could actually consider is that maybe, first of all, the oxygen first has to split into 2 separate atoms like this. And what you will get is one of the carbons joining with one of the oxygens, first of all. So that will give us the product CO. So I would then have this 1 carbon atom joined with 1 oxygen atom. And that would leave me with just half of the O2. So I've only got 1 of the atoms of O2 left. So I've got half of an O2. So if this is a full O2, then one of them is a half O2. So I've got CO plus a half O2. So this could be step 1 of the process. And in forming carbon monoxide, we would have a delta H equal to minus 110.5. So forming carbon monoxide from carbon and oxygen has a delta H of minus 110.5. What would then have to happen is the other atom of oxygen, half the O2, the other atom would have to join as well. So this would be step 2. So the other atom would then join together to make the full product. So now we have the 2 oxygen atoms joined to give carbon dioxide. Now, like I said, we can consider this as happening in one step. Just the 2 atoms join straight on, and that's root 1. But root 2 shows us that the reaction could happen in 2 steps. And step 2, where the second atom joins CO to make CO2, has a delta H equal to minus 283. Now, it so happens that if we take root 2 and we add up the energy changes from the 2 steps, we would get minus 110.5. So we're taking this one here, bringing it over here. And if we add it to the energy from step 2, minus 283, we get a total energy change, total delta H, of minus 393.5, which, funnily enough, is the exact same as the delta H you get if you measure it in only one step. So delta H equals minus 393.5. So the story here is that it really doesn't matter if the reaction happens in 1 step or 2 steps or 3 steps, the overall energy change is going to be the same. And that gives us this rule here. So the heat change for any reaction, it really does not matter. It does not depend, or the heat change for any reaction, we say it is independent, because it does not depend. Independent of what we say the pathway taken. What we mean by the pathway is if it happens in 1 step or 2 steps, or 3 steps. So like root 1 or root 2 here. So is independent of the pathway taken. This rule is what we call Hess Law. And Hess's Law is really neat because it allows us, because this rule always stands true, it allows us to work out, I'm just going to make that a little bit neater, allows us to work out delta H's for reactions that we might not be able to measure directly. So we might only be able to measure one step or two steps or two different steps of a reaction, and we can use it to work out the overall delta H change. Now, why might that be the case? Well, we might not physically be able, for some reason or other, to actually get in and measure the temperature change in a particular reaction. But often we can use numbers from different steps of the reaction to help us work out what the total energy change would be. Okay, so that's Hess's law, is that heat change for a reaction is independent of the pathway taken. It's time for you guys to do some practice now. So, I'm just actually going to leave that there. I'm going to ask you to quickly pause the video, take that down. So take that down as a definition that must be learned. Okay, so you should only be playing the video if you have the definition down now, and it's time to do some practice. Okay, right. So I've got some keywords, or I've got a paragraph for you guys to write down and fill in the keywords for me. So what I want you to do is I want you to write the full paragraph, try and fill in the keywords in the blanks for me, please. So do that now. Okay, so you should only be listening to my voice now if you have written the paragraph and you have tried to fill in the blanks. And it should be pretty easy if you are listening to the explanation and if you've watched the other videos. So during a chemical reaction, the bonds in the reactants, that should be reactants, get broken before bonds in the products are formed. So bonds in the reactants get broken before bonds in the products are formed. Energy is taken in from where? Well, it gets taken in from the surroundings to break bonds. So bond breaking is endothermic because energy is taken in, so endothermic. Energy is transferred to the surroundings when bonds are broken, or when bonds are formed, sorry. So bond formation is exothermic. No energy is, well, that would be created or destroyed when a chemical reaction occurs. This is known as the law of conservation of energy. Reactions can happen in one step or multiple steps, but the energy change overall does not depend on the pathway taken. This is known as Hess's law. So here is the written down answers. If you need to copy them down now, if you need to fill in any mistakes you made, do that now. And I've got some more practice questions for you guys to do now. All right, so there's some retrieval questions here, and then there are some questions from today. Sorry, this should say, I'm just going to change that one, should say question 4, and this should be question 5. Okay, so pausing the video, I'm doing that now. Okay, so the first question is the heat of reaction. This is just a straightforward definition. It's the heat change. Here it is, I'll show you it written down. It's the heat change of a reaction is the energy change when a reaction occurs in the molar quantities described in the balanced equation. So once you have your equation written down, balanced, whatever the molar ratio is, when the reaction happens in that molar ratio, that tells us whatever the heat change is during the reaction, that is the heat of the reaction. The second question says, define the law of conservation of energy. So the law of conservation of energy states that energy cannot be created or destroyed, only change from one form to another. So you have to complete the following sentences then. Bond breaking is an endothermic process, that should be, and bond forming is an exothermic process. So check them there. There we go. Number 4. Sorry about this now. Sorry, my screen's just gone a bit funny here. I don't know why. Give me a sec. Okay, so number 4 says, consider the following reaction, demonstrate an alternative route that shows the reactants forming the elements before forming the products. So this is what you should have. Well done if you got this right. C6H14, well, plus 9.502, you should have 6C plus 7H2 plus 9.502 as the elements in root 2. Well done if you got that right. And the last one, Hess's law can be used to describe the process shown in question 4. Define Hess's law. There it is there. Question 5 is the definition. Okay, I hope you found today's video useful. In the next video, we're going to jump more into the actual calculations part of it, where we can apply Hess's law to work out some heats of reaction. So I will see you in the next video.